Okay, our second example. Y double prime plus 5y prime plus 7y equals 0, with y of 0 equal 1, y prime of 0 equals negative 1. Very similar to our last equation, except in our last equation this plus 7 was negative 6. Our initial conditions were the same as what we have here. And these initial conditions are fairly simple conditions to handle numerically and algebraically. But the process is pretty much the same no matter what the initial conditions might be. So we assume y equals a e to the RT. And I'm not going to write out all the details here. We get the characteristic equation r squared plus 5r plus 7 equals 0. With solutions, we're not going to factor this one. We're going to have to use the quadratic formula. We're going to get negative 5 plus or minus the square root of 25 minus 4 times 7 over 2 equals negative 5 plus or minus the square root of 3 over 2, square root of negative 3 over 2, which is negative 5 halves plus or minus the square root of 3 over 2 times I. From this we find that our values of y, y is going to then be a e to the negative 5 halves plus the square root of 3 over 2, square root of 3 over 2 I multiplied by t plus b e to the quantity negative 5 halves minus the square root of 3 over 2 times I multiplied by t. Applying the laws of exponents, we have a e to the negative 5 halves t times e to the square root of 3 over 2 I t plus b e to the negative 5 halves t e to the negative square root of 3 over 2 I t. We see that the e to the negative 5 halves t will factor out, so we can write this as e to the negative 5 halves t multiplied by a e to the square root of 3 over 2 I t plus b e to the negative square root of 3 over 2 I t. Now, applying Euler's identity, e to the square root of 3 over 2 I t is cosine of square root of 3 over 2 t plus I sine square root of 3 over 2 t. So, writing that out, we have a times cosine square root of 3 over 2 t plus I sine square root of 3 over 2 t, and then plus b times e to the negative square root of 3 over 2 I t, which, as we've seen previously, is going to give us something like cosine of square root of 3 over 2 t minus I sine square root of 3 over 2 t. The details have been discussed before. Very simple. If we have the negative here, the cosine of negative square root of 3 over 2t is equal to the cosine of the square root of 3 over 2t because the cosine is an even function. The sine of the negative is the negative of the sine because of the odd nature of the sine function. Now, if we simplify a little further, we see that we have both an a and a b times the cosine of the square root of 3 over 2t, and I times a times the sine square root of 3 over 2t, and b negative b times the sine of square root of 3 over 2t. We can write this as then y equals e to the negative 5/2 t multiplied by quantity a plus b cosine square root of 3 over 2t plus I times a minus b sine of the square root of 3 over 2t. Now, as we've seen before, a plus b and a minus b can be set equal to any two constants that we want, including complex constants, so that this general solution can be put into possible forms. Y of t equal e to the negative 5/2 t times c cosine square root of 3 over 2t plus d sine square root of 3 over 2t, or y of t equals e to the negative 5/2 t multiplied by, let's say, c times the cosine of square root of 3 over 2t plus phi. Again, we've seen some of the details of this rearrangement before, so we're not going to belabor them at this point. I'll note that I just made a change here. I'm going to call these constants C1 and C2 so we don't confuse the C1 and C2, or the C of the C and D with the C we have down here.